Before an engineer builds a bridge, what do? They measure. Before a surgeon begins an operation, what do? They measure. And before a team of engineers launches a spacecraft to Mars, they measure. Very, very carefully. Because in 1999 a NASA spacecraft worth $327 million disintegrated as it approached Mars. The reason? One engineering team used metric units, another team used imperial units, and nobody caught the mistake. Physics is the language of the universe. That language is written with numbers, units, and vectors. Today, we learn the alphabet of that language, SI units, dimensional analysis, and vectors. In science, we use a shared language called the SI system, the International System of Units. The SI system defines 7 base quantities, each with its own base unit. First, mass. The unit is the kilogram. 1 kilogram is roughly the mass of 1 liter of water. Second, length. The unit is the meter. Third, time. The unit is the second. Fourth, electric current. The unit is the ampere. Fifth, thermodynamic temperature. The unit is the Kelvin. Sixth, amount of substance. The unit is the mole. And seventh, luminous intensity. The unit is the candela. In this course, we will mostly work with the first 3, kilogram, meter, and second. Together they form what is called the MKS system. Now, let's look at derived units. These are units built from the base units. For example, velocity is meters per second. Force, the Newton, is kilogram times meter per second squared. And energy, the joule, is Newton times meter, which works out to kilogram times meter squared per second squared. What about very large or very small quantities? We handle those with metric prefixes. Nano means 1 billionth. Micro means 1 millionth. Milli means 1,000th. So 1 millimeter is 1,000th of a meter. Kilo means 1,000, so 1 kilogram is 1,000 grams. Mega means 1 million. Giga means 1 billion. Because of this prefix system, we use scientific notation to write very large or very small numbers cleanly. For example, the thickness of a human hair is approximately 70 micrometers, that is 70 times 10 to the power of -6 meters. Finally, significant figures. These tell us how many digits in a measurement are actually reliable. For example, a measurement of 2.53 meters has 3 significant figures. When calculating, your answer should be rounded to match the fewest significant figures in your input data. Now, let's talk about dimensional analysis, one of the most powerful tools in all of physics. Every physical quantity has a dimension. The dimension of length is written as capital L, mass as capital M, and time as capital T. The first rule of dimensional analysis is this: both sides of any physics equation must have the same dimensions. If they don't, the equation is simply wrong. Let's verify an example. Velocity equals displacement divided by time. Dimensionally, length divided by time. That gives us meters per second. Correct. Another example, Newton's second law, force equals mass times acceleration. What is the dimension of acceleration? Length divided by time squared. So the dimension of force is mass times length divided by time squared. That is kilograms times meters per second squared, exactly what a Newton is. Confirmed. The second power of dimensional analysis is estimating formulas from scratch. Suppose we know that the period of a pendulum depends only on its length and gravitational acceleration. The dimension of length is L. The dimension of gravitational acceleration is L over t squared. We need the result to have dimension t. The only combination that works is the period equals some constant times the square root of L divided by g. That constant turns out to be 2 pi, confirmed by experiment. This method does not give the exact answer, but it gets you remarkably close, using nothing but logic. Dimensional analysis is also indispensable for unit conversion. Say we want to convert 60 kilometers per hour into meters per second. Multiply by 1,000 meters per kilometer and divide by 3,600 seconds per hour. The result is 16.67 meters per second. There are two types of quantities in physics, scalars and vectors. Scalar quantities are described by a single number, a magnitude, temperature, mass, energy, speed, time, all scalars. Vector quantities have both a magnitude and a direction, force, displacement, velocity, acceleration, momentum, all vectors. Why does this distinction matter? Because the rules for adding vectors are different from the rules for adding scalars. Think about it this way. You walk 3 steps east, then 4 steps north. The total distance you travelled is 7 steps. But your displacement, how far you are from where you started, is not 7. It is 5. Because displacement is a vector, and you must use the Pythagorean theorem. Vectors are drawn as arrows. The length of the arrow represents the magnitude. The direction of the arrow represents the direction. In mathematical notation, vectors are written in bold or with an arrow above the symbol. The most practical way to work with vectors is to break them into components. Imagine a vector A in a coordinate plane. Its magnitude is A and it makes an angle theta with the positive x-axis. We decompose it into 2 components. The x component, a times cosine theta. The y component, a times sine theta. Going the other direction, if you know the components, you can find the magnitude using the Pythagorean theorem. The square root of x squared plus y squared. And the angle is the arctangent of the y component divided by the x component. Now for vector addition. To add 2 vectors a and b, we simply add their components separately. The x component of the result equals the x component of a plus the x component of b. The y component works the same way. Then we compute the magnitude and direction of the result. The beauty of this method is that it scales to any number of vectors. Add as many as you like, no geometric drawing required, just components, arithmetic, and Pythagoras. We also have the dot product or scalar product. A dot B equals the magnitude of A times the magnitude of B times cosine of the angle between them. This gives us a scalar, and we will use it extensively when we study work in a few weeks. And the cross product, or vector product. The result is a new vector perpendicular to both A and B. This will become important when we study torque and angular momentum later in the course. Let's consolidate everything with a problem. A person walks 5 meters in a direction 37 degrees north of east. Then they walk 8 meters due east. What is the magnitude and direction of their total displacement? Step 1. Decompose each vector into components. First vector, magnitude 5 meters, angle 37 degrees. X component 5 times cosine 37 degrees. That is 5 times 0.8, which equals 4 meters. Y component 5 times sine 37 degrees. That is 5 times 0.6, which equals 3 meters. Second vector, 8 meters due east, entirely along the x-axis. X component, 8 meters. Y component, 0. Step 2. Add the components. Total x, 4 plus 8, equals 12 meters. Total y, 3 plus 0, equals 3 meters. Step 3. Find the magnitude. Square root of 12 squared plus 3 squared. That is the square root of 144 plus 9. The square root of 153, approximately 12.4 meters. Step 4. Find the direction. Arctangent of 3 divided by 12 equals arctangent of 0.25. Approximately 14 degrees north of east, so the person ends up approximately 12.4 meters from their starting point, in a direction 14 degrees north of east. Today we covered 3 foundational topics. First, the SI unit system, 7 base units, derived units, and metric prefixes. Second, dimensional analysis, how to verify equations dimensionally and how to estimate formulas using nothing but the dimensions of the quantities involved. Third, vectors. The difference between scalars and vectors, how to decompose a vector into components, and how to add vectors cleanly using components. Next week we move into one-dimensional kinematics, position, velocity, acceleration, and free fall. Everything we learn today builds directly toward that. I've left practice problems in the description below. Work through them before the next video. If you have questions, leave them in the comments.